Section 8 takes what we did in the last section, proportions, and applies it to like real life stuff. So you use proportions all the time when you're working with scales. Scale drawings, scale figures, scale models, things like that. So that's what we're doing here. If you need to know a missing length on a similar figure, similar basically means that you have the same exact shape, but they're not the same size. So like a scale model of I don't know, a car or something. Exact same proportions, but it's just smaller. Okay, I'm sure you've all worked with scale models before, you've seen them before, so you know what I'm talking about. All right, we have a sailboat, like a real life sailboat, and then an accurate model of that same sailboat are shown. What is the length of the model sailboat? What is it? 3? Okay. So we know how to work with similar figures, but how did you do that? The answer is 3. Okay. So in geometry class next year, when you guys take geometry, you're going to learn about something called a scale factor. To go from here to here, we are dividing by 3 or multiplying by a scale factor of 1/3. Okay. This model here is 1/3 the size of this model. So all the dimensions here are divided by 3 here. And you'll see scale models on blueprints and things like that. Okay? So to go from here to here, we're dividing by 3, which means every dimension can be divided by 3 to go from here to here. 9 divided by 3 is 3. So that's the answer. But you can set this up using a proportion. If you remember from last time, we can set up proportions as long as we have all the same stuff on all the same sides. So left side, right side, top, bottom, those things all have to kind of line up. So I can set up a proportion here. What do you want to put on the left ratio? What's that? So what is going on that left ratio? What is that? Where'd you get that information from? Well, which one? We have 2. Yeah, but where did that come from? Big sailboat. So that means we're putting the big sailboat on the left, which makes the little one on the right. And you keep telling me 12 over 9. So the big sailboat has 12 over 9. But what is that 12? It's the height. So the height is going on top of my proportion, which means that the length is going on the bottom. So for my little sailboat then, I have to put height up top and length on the bottom. The height of the little sailboat is 4, and the length is, I don't know, so I got to call it x. Okay? Now we've set up that proportion correctly. Now, like I said last time, you don't have to put these labels on there like this. I'm just showing you that because that's how you set up a proportion. Once you are able to set up proportions like this, then you don't need to write those labels, but they do help. So now how do we solve this proportion? Yeah, so what's that called? Cross products property. So we do 12 times x, which is 12x, equals 4 times 9, which is 36. And then we solve for x by divide both sides by 12, and we get x equals 3. 3 what? Feet. In the end, make sure you have your labels on there, okay? So we did come up with the correct answer by looking at this. And you guys have worked with things like this before, so that is math that you can probably do in your head. But this is the official math. This is what you did in your head. You set up the proportion, and then you solved it. Even if you don't think you did, that is what you did. Believe it or not. All right, a little bit of notation we need to learn. This symbol right here looks like a little squiggle or something. That means that we have 2 figures that are similar. So you'll be working with that symbol a lot next year in geometry, but you will see it from time to time also in algebra, and of course we're seeing it here. So in the diagram, what does that mean right there? Triangle ABC. So here is ABC. We're talking about this triangle here is similar to, good, triangle FGH. So that means that this triangle, if I apply a scale factor to it, if I multiply everything in that triangle by some number, I'll wind up with exactly this triangle, okay? Now, we might not know exactly what that number is. In this class, it doesn't really matter. All we have to do is, once we see that things are similar, we need to realize that we can set up a proportion to find missing sides. So, in similar figures, the measures of the corresponding angles are equal, and corresponding lengths, side lengths are in proportion. That word proportion tells me that I can set up a proportion to solve for any missing side length. So if I use geometry, this first part here says the measures of all the corresponding angles are equal. So that means this angle right here, B, is going to be the same measure as this angle right here, G. And that's how we would note that in geometry. The angle A is going to be exactly the same measure as the angle F. And that's how we'd note that in geometry, because I already used the one little arc. The angle C is going to be the same measure as the angle H, and I've already used one arc and two arcs, so now I'm going to use three arcs to represent that. Have you seen that before? Like in 8th grade math or something? Okay, good. And the reason that I know that A is the same measure as F is because of the way that it's written here. A comes first in this, F comes first in this, so that's why I know that these two angles right here are the same measure. B comes second, G comes second. B, G, and then finally C, H. So there is a reason why these letters are arranged in that order. It's not because they're alphabetical. It's because those angles match up from one triangle to the next. Okay? So keep that in mind too when you go to geometry. That'll help a lot. The orders of the letters when you name similar figures is important because I just told you all that. So because triangle ABC is similar to triangle FGH, the following things are true. Angle A, this looks like an equal sign. It's hard to see on here. With that same squiggle over the top of it, that means congruent. It means they have the same measure, okay? They are the same. So angle A is the same as angle F. Angle B is congruent to angle G, and that's what we labeled up here. Angle C is congruent to angle H, and again, that's what we labeled up here. So that is all true stuff. The reason you need to know that is because I could give you two triangles. Here's one like this, and then here's another one like this. If I call this one A, B, C, and this one D, E, F, then I would have to say, if these are similar triangles, that triangle ABC is similar to triangle, looks like D, but then FE. Okay? Not just alphabetical order. A goes with this angle, B goes with what looks like the right angle, so that's got to be F. I wrote A, B, C, so then I have to write D, F, E. So just be careful about that. The other thing that's important here is that guy right there. Those are three proportions, and actually you can write a whole lot there's a lot of proportions that you can write from similar triangles. These are the ones we need to talk about here. We have AB over FG, and that's in green. So I'm going to put a green line here, AB over FG. So those are corresponding sides. They are in proportion. The next one we have is the blue one, AC over FH. So AC is here, and then FH is here. Those are corresponding sides, which means they are in proportion. And finally, we have in red the BC over GH. So that's that guy right there and that guy right there. Those sides are in proportion. So now if I take that idea and I make these ratios here of all of these sides, then my green ratio will be AB over FG. Well, AB is a length of 8, over FG, which is a length of 12, equals my blue guy, which is AC, which is 10, over FH, which is 15. So I got that ratio, equals, and then finally my red guy, which is BC, which is 12, over GH, which is 18. Those are my three ratios that they're telling me. Is this true? 8 twelfths equals 10 fifteenths equals 12 eighteenths. Is that a true statement? Yes. 8 twelfths reduces down to what? Two-thirds. 10 fifteenths reduces down to what? Two-thirds. And 12 eighteenths reduces down to, again, two-thirds. Okay? So you can write proportions like this, and you will have a true statement as long as the two triangles are similar to each other. And that's what we're working with in this section. Scale models are similar to each other, just like these triangles are similar to each other. All right, so let's do some problems here. We have a multiple choice question. That's great. In the diagram, it says triangle ABC is similar to triangle DEF. What is DE? What's that length? So let's set up proportions here using similar sides, corresponding sides, write a proportion. Okay? Now, I will one more time tell you to make sure that you set up your proportion correctly, which means we have side lengths that need to be on the correct location, top or bottom, or left or right. We have triangles that need to be in the correct location, either top or bottom, or left or right. Just depends on how you want to set it up. So I'm going to write my proportion like that, and then I'm going to decide what I want to put on the left and what I want to put on the right. So what do you want to put on the left? Do you want to put triangles on left and right, or do you want to put side lengths on left and right? Okay. So we are looking at DE. We're looking for that side right there. That corresponds to that side right there. Right? Okay. So then we need some other two sides to give us some help on that proportion. So I'll highlight those sides in red. On this triangle, we only know one other side. This side right here. BC. What side does that correspond to on the other triangle? EF, that's right. Okay, so now we can set up this proportion. I can put my red sides on one side and my blue sides on the other. Or I can put all of my information for the left triangle on the left side and all of my information for the right triangle on the right side. It doesn't matter. Just make sure you're consistent. So what do you want to put over here? Blue, red, or left side triangle? Blue? Okay. So then that's going to mean that this has to be top or bottom and this has to be top or bottom. Okay? So I mean not top or bottom, but left side or right side. So if this is going to be blue sides, this is going to be red sides, what do you want to be in the numerator? Left side triangle or right side triangle? Okay, fine. Left side triangle and right side triangle. Again, it doesn't make any difference. You could set this up so that the left triangle is this guy and the right triangle is this guy. And then blue here and red here. As long as you set it up right, you're going to be fine. So, for my blue sides, the left triangle has a length of 10. And for my blue sides, the right triangle has a length of, don't know it, so I got to call it X. For my red sides, the left triangle has a length of 16. And for my red sides, the right triangle has a length of, which is it? 12. So that's your proportion. Cross multiply, and you get 120 equals 16x. Divide both sides by 16, what do we get? Fifteen halves equals x. So now we go back to the problem and we say, all right, it was a multiple choice problem. I got to write my answer down. What's my answer going to be? 7.5. So the answer is A. You'd bubble in A. I'm just circling it, but you would fill in the bubble. All right, so now that is the original problem, and I'm asking you a different problem now. In the figure above, what is AC? These are still similar triangles, so you solve it the same way. Go ahead and set up a proportion and solve. Find the length of AC. All right, let's set this one up. There's a number of ways that you can set this problem up. I want to set it up a couple of different ways to show you that there are different ways to do this, okay? Just like up here before, let me erase these lines so that we're not confused. I need this side here, so I'm going to call that side my x. So I know that length and that length. I'm looking for that length and that length. So those are the sides that I need. BC, AC, EF, DF. Set it up however you want. There's going to be a proportion, but once you start setting it up, the rest of it all falls into place. So I could say BC divided by AC. I took this length here that I knew, divided by this length here that I didn't know. Now I got to go across my proportion, so I'm going across to my other triangle, and I'm doing exactly the same thing. This corresponding side divided by that corresponding side. 12 over 18. Or I could have set up a different proportion and done it just like I did this here. This time I'm doing the left side over the right side. So the left would be 16 over 12 equals the other left side over the right side. So that would be x over 18. BC over AC here, was 16 over x. So I get rid of that. So now I have that proportion instead. There's a number of proportions that you can set up here. There's actually 6 of them. They're all correct. It's just a matter of which one you decided to do. So since I have this one sitting here, I'll go ahead and do this. When we cross multiply, we get 12x equals, what's 16 times 18? 288. Okay. Then we divide both sides by 12 and we get x equals 24. Everybody, when they did their proportion and then they cross multiplied, did everybody get 12x equals 288? Did you get x equals 24 in the end? So that's why. But no matter what proportion you used to set it up, as long as you set it up correctly, when you cross multiplied, everybody got the same thing. And then from there, you divide both sides by 12. Unless you saw that this 12 over 18 reduces. 12/18 reduces down to what? 2/3. So this actually could become 16 over x equals 2/3. And now when I cross multiply, I get 2x equals 48. Divide both sides by 2 and we get x equals 24. Same answer. Okay? There are a ton of different ways to do these. Just set them up correctly and then you will get the right answer in the end. This problem could be straight out of a geometry book, actually. It comes out of the algebra book, but this is basically geometry. Geometry, ACT, things like that love to throw problems that look like this at you. The sun's rays strike the building and the girl at the same angle. That should make sense to you. We got the sun way up here, right? And it's shining down. So the sun is making the building cast a shadow, the same as it's making the girl cast a shadow. Okay? Now maybe this building is so tall that we can't measure it. Like I can't just sit there and stack ruler after ruler up here and wind up with the height of the building. That wouldn't work. Okay? But what we can do is measure the shadow length of the girl and measure the shadow length of the building. That's easy to do. Then we measure the height of the girl And because of the fact that this light source doesn't move, we can then use similar triangles to determine the height of the building. And you guys ever been like going down the road with your family or something like that, and you see survey crew, and there's some guy with like a post standing there? You'll see a sign that says survey crew, and then there's some guy standing there with like this post thing, and then maybe like a mile down the road or something, there's some other guy standing there, and he's holding this tripod, and there's this thing that he's looking through back in the direction of that post. He's using similar triangles, actually, to measure elevations and things like that. It's a very basic way that this math that you're learning right here is used every single day all over the world. So then those guys actually make a decent amount of money. So you could be part of a survey crew, and you will be doing things like this, using triangle math to solve real-world problems, like for construction and engineering projects and stuff. And actually, if you watch the construction project going on over there, you might see this situation. There'll be guys taking surveys and making sure that things are level and stuff, and they can do that using similar triangles very easily without having to like measure for miles and miles and miles. All right, let me get that out of there. We have the sun's rays striking the building and the girl at the same angle, forming the two similar triangles that we see. So the side length here is 3, the side length here is 5. Then we measure the shadow length and we get 15 feet. We can now set up a proportion to figure out what the height of the building is. So let's try to set that up. What should I do? So let's draw in the little stuff, right? Okay. You're calling this x because they called it x. So x over 5. He's comparing sides, and he's saying, okay, the building's height compared to the girl's height, x over 5. So what is going on this side of the proportion? What is that? So these are the heights, which makes this side have to be what measurements? The lengths of the shadows. Okay, so on top we put x, and x corresponds to which figure? So that would be the what? What is this thing? It's the building. So the top is the building, and the bottom is the girl. Okay? So that's how we placed it. The x over the 5 determined all of these things. So now that we have that, we now know what has to go here. On top has to go the length of the shadow of the building, which is 15, and on the bottom has to go the length of the shadow of the girl, which is 3. And now the proportion is set up correctly. How can we solve this? You could multiply by 5 to both sides, and that'll get x by itself. You could cross multiply and get 3x equals whatever 15 times 5 is. 75. The easier thing to do here is going to be to multiply both sides by 5, because that gets x by itself in one move. X equals, now I have 15 times 5 divided by 3. Well, 15 divided by 3 is 5. And then 5 times 5 is 25 what? Feet. So that building is 25 feet tall. I didn't even have to measure it, but I know that it's 25 feet tall because I used geometry and a little bit of algebra to figure that out. You could do this for a tree. You could do it for a telephone pole. You could do it for the Empire State Building. It always works, and it will give you a perfectly accurate answer. Yeah, you just got to make sure you measure your height right and your shadow length. But yeah, otherwise you'll get a perfectly good answer. Okay, a man who is 6 feet tall is standing next to a flagpole. The shadow of the man is 3.5 feet, and the shadow of the flagpole is 17.5 feet. What is the height of the flagpole? Very similar problem. Go ahead and give that one a shot. The nice thing about learning proportions this way is you don't even need a figure. We have a man, and we have a flagpole. We have the height of the man. We have the height of the flagpole, which is what we don't know, so I'll call that x. we have the shadow of the man, and we have the shadow of the flagpole. All the information that we need in this problem is given to us. We don't even need to draw a figure. If you need to draw a figure, draw a figure. A picture always helps. You don't really need it here, though. Set up your proportion and just start placing numbers. What should I put here? Okay, I heard x over 6. So x would be the height of the flagpole. 6 would be the height of the man. So on this side, I'm talking about height. Which means on this side, I better be talking about the shadow. On top, I was talking about the height of the flagpole. So that means over here, I better be talking about the height of the shadow, or the length of the shadow. So what is the 17.5? And therefore, the length of the shadow for the man, 8.5. Oh, sorry, 3.5. So then we cross multiply if you want, or in this case, because the x is on top, you can just multiply both sides by 6. And that's what I prefer to do here because it saves me some work. Now I can just type into my calculator 17.5 divided by 3.5 times 6. And I get x equals what? 30 what? Feet. There's your answer. This is a very real world thing that we could do. If we're outside on a sunny day, I could have you measure something. Would that be a reasonable thing for me to ask you to do? Determine the height of something tall? Could you do it? If you had a calculator? Yeah. And if you had maybe some measuring tape or something, right? You could do it though. Okay? All right. So like I've been saying, we use proportions all the time in real life. We use them on maps. You've been using them on maps. We use them on blueprints. Most of you probably haven't used blueprints before, but we use them on blueprints. And also on floor plans, like when you guys move into an apartment. You can look at a floor plan and kind of get an idea of what the apartment's going to look like without even having seen it. We have a couple of vocab words here. Scale drawing and scale. So scale drawing is just a drawing that's similar to an actual thing. It's a drawing that's similar to a real life thing. And I'm just putting a real life thing in there because we could be talking about a building, we could be talking about like a model car, we could be talking about a model human being. Like veterinarians would maybe use a model cow. Massage therapists use model people all the time. Scale is very similar to scale drawing. A scale is just the ratio of the drawing to real life. And maybe it's not a drawing, maybe it's a model, a scale model. The scale there is the ratio of the size of the smaller thing to the size of the larger thing. So the most common way to use scale or scale drawings is on maps. We have a map here of the top half of Florida. Jacksonville, Florida is sitting right here. And then it says, what is the actual distance from Jacksonville to Orlando? Orlando is sitting down here. So on the map, Orlando is there, and Jacksonville is here. And in this drawing, they're giving you like a ruler. Like somebody put a ruler down and they measured how far it is from Jacksonville to Orlando. Now also in the map, on any map, you're going to see a scale. The scale there says 1 inch to every 110 miles. So on the map, 1 inch corresponds to 110 miles in real life. Okay? So what we need to do is measure on the map how far Jacksonville is from Orlando. Once we have that length, then we can compare it to the scale, setting up a proportion, and then solve to find out the real life distance from Jacksonville to Orlando. Straight line distance, not necessarily by car. Okay? So, we have this scale. 1 inch is 110 miles. So 1 inch is 110 miles equals. And notice when I put those units on there that it really helps me set up my proportion correctly. So over here, I'm going to measure how far on the map it is, and I'll have inches over miles again. This is the map scale. This is the real life. Okay? So how far is it on the map from Jacksonville to Orlando? We need to look at what the scale is here, right? We have 0 to 1 all the way to there, and then it looks like Orlando hits right on one of those longer hash marks. Is that a half or a quarter? That is a quarter. Look at how far a quarter is here. We have 3 little marks and then the quarter mark. Here we have 3 little marks and then the quarter mark. So that is 1 1/4. So 1.25 inches. And what will go here? X. How far is it in miles in real life? Okay? So now we simply cross multiply. We have x times 1, which is just x. That's nice. We don't have any math to do after that. And then we have 1.25 times 110. Just multiply that out and we'll have our answer. What do we get? 137.5 what? Miles. Okay? Because we know that x has to be in miles here. So that's the answer. That's how you use a scale drawing, like related to a map. Okay? Use the scale that you're given on the map, and then measure the map, and you'll have your answer. All right, down below it says the distance between Jacksonville and Gainesville. So now we're talking about the same Jacksonville here, but Gainesville now is over here. On the map is about 0.6 inches. So what is the actual distance from Jacksonville to Gainesville? What do we do? So we better, before we do that, do what? Well, they're telling us. So they've told us that it's about 0.6 inches. So that's like we measured it and we got 0.6 inches. So I don't want to just go into trying to write an answer. That's not what algebra is all about. And if you're doing that on your homework, you need to stop. Actually write down the problem. What do? The proportion. So I'll put that equals that. One inch over 110 miles. The same scale, it's the same map. Equals 0.6 inches, the thing we measured, over how far is that in real life. Okay? So now it's set up. Now you can do that cross multiplying. 1 times x is x equals 110 times 0.6. 66 miles. And I could ask you anything on here. I could give you the measurement, or you could measure from Tallahassee to Jacksonville. You can measure from Tallahassee to Orlando. Any of those distances will be able to be solved using this proportion, using that scale that we have on the map. Another way to use proportion is on scale models. A scale model now, instead of a scale drawing, is just a model that is an exact replica. That is exact but smaller. Or maybe a scale model of an atom would be exact but much larger, so that we can actually work with the thing. So we have a giant model heart. This is a picture of a giant model heart. If you were to stand here, you'd be about that tall probably. It's 14 feet tall. The heart is the ideal size for a person who is 170 feet tall. Of course, that's never going to happen. But what side would you expect the heart of a man who is 6 feet tall to be, given that ratio? Okay? Again, very simple problem to set up here. We have 14 feet. For the heart, corresponds with 170 feet for a person with a size heart that big. So x feet for the heart of a normal sized person who is 6 feet tall. There's your proportion. Multiply both sides by 6. X equals So decimal that? 0.49 feet. So like half a foot, about 6 inches, okay? So that's the average size of a heart for a 6-inch tall person.